Hello! Today I'm going to show you how to solve a set of simultaneous equations that involve two linear equations. So the method we're going to use is we're going to try and make sure that one of the variables has the same coefficient in each equation. That way we can subtract one equation from the other one, leaving a new equation with the other variable and just some constants. So we should be able to solve that one, find that variable, and then plug it back into one of the original equations that we had. So looking at this, we'll start with one set and we'll have 5x plus 3y is equal to 41. And the other equation will be 2x plus 3y is equal to 20. So these two together are our set of simultaneous equations. And we can see here that already the variable y has a coefficient of 3 in each equation. So therefore we've kind of done step one already. It was done just in the way the question is set up. So now we're going to subtract one equation from the other equation. And we can do that in the same way you do subtraction normally. We'll go sort of term by term. The 41 minus the 20 will give us 21. 3y minus 3y is 0. So that's very useful. That's exactly why we want to have the matching coefficients, so that we eliminate this variable when we go down to the new equation. And 5x minus 2x gives us 3x. So what we're left with effectively is 3x is equal to 21. And if we divide both sides by 3, we're left with x is equal to 7. So that's the value for one variable. And now we're going to take this value and plug it back into either equation, doesn't matter which one, and find a value for y. So we'll plug it back into this second one. So we get 2 times 7 is 14, plus 3 times y is equal to 20. Taking 14 from both sides, and we're left with 3y is equal to 6. And then dividing by 3, you get y is equal to 2. So the final solution to our set of simultaneous equations is 7, 2. Beautiful. We'll have a look at an example where it's not already matched up. So here the 3 and the 3 were matched up, and we'll have a look at one where it's not matched up. So in this set of equations we have 2x plus 4y is equal to 26, and also 3x minus y is equal to 4. Now it doesn't matter which variable you choose. In the example here we had y matching up. In this one we could have x or y, doesn't matter as long as you always get the same variable to match up. So it could be like x and x and y. You couldn't have a situation where you've got 4x and 4y. That wouldn't be useful at all. So thinking about this then, it might be easier here to multiply the bottom equation by 4. So we multiply every term by 4 and we end up with 12x minus 4y is equal to 16. Now you'll notice here we've got positive 4 and here negative 4. That's okay. Whereas above here we did a subtraction, now we're going to do an addition. The idea being that the 4y plus a negative 4y, so 4y minus 4y, is going to be 0. So the whole goal is to eliminate one of the variables. It's not just to do a subtraction, but it's to eliminate one of the variables. So we'll do that then. We'll kind of rewrite this so we can see everything again. So we can have 2x plus 4y equals 26, just writing everything above the other variable, no change in that there. And adding these two together then, well 2 plus 12 gives us 14. 4 minus 4 gives us 0, okay, 14x there, plus 0y is equal to 42, adding those two together. So we're left with 14x is equal to 42. If we divide both sides by 42, we're left with x is equal to 3. So we found the value for x. Now we can substitute that back into one of the equations. This one looks a bit simpler. Doesn't matter again which one you choose here. You can pick either one, should give you the same answer. And what we get then is 9 from the 3 times 3 minus y is equal to 4. So adding y to this side and taking 4, we get that y is equal to 5. So our final answer is going to be 3, 5. Beautiful.